Hey, Mr. Younger, I had a question for you.
Yeah, what's up?
So, face-to-face test three and the final are separate exams, correct?
Yes. Yes, you have a face-to-face test three that's due by Tuesday of next week. If I remember correctly, check your announcements and emails that I sent for that to confirm, but I think it's due by Tuesday of next week. And then your final exam, which can be taken probably about as early as Tuesday of next week, but is due by noon on May the 4th, which is a week from Monday.
Sorry, my internet like blipped out and I
Okay.
I couldn't see or hear anything. What were you saying?
No problem. So yeah, again confirm my dates by emails or announcements that I posted. But if memory serves me, I have set up the face-to-face test three, which is a different test, but is a face-to-face one. I've set that up so that you have to have it done by Tuesday of next week. Uh, at a testing center or through various Zoom appointments that I've offered, or you could have came today and taken it as a few people did. And then the final exam probably can be taken as early as Tuesday of next week, but has to be done by May 4th, which is a week from Monday, and it has to be done by noon on that day. And that also has to be proctored. And therefore, you either have to hook up with one of my Zoom sessions or you have to attend my class, which I'm giving my exam on Wednesday. So you have Wednesday that you could go and do it on campus at the Virginia Beach campus, or you have to book an appointment at a testing center, or you have to book an appointment with me at one of my Zoom sessions.
Okay, thanks. I was just trying to get some clarification because with the announcement, I remember you saying something about like one of them being due early May, but the announcement I was reading it said they were both due next Tuesday, and with my work schedule, it's kind of hard to get in for the proctoring and stuff like that. So,
Gotcha. That's why, yeah, that's why I sent it out last week to give y'all plenty of time about that. But what I was saying was, even though the face-to-face test is due by Tuesday, I was leaving it open longer because that was the same practice test for the final. So that was the reason why there seemed to be some confusion. I wasn't saying they were the same tests. I was just saying that you can use the same practice test for it. Actually, and I might be remembering what I said about 242, not 241. Let me double check that part. But either way, yeah, there's definitely two tests about it. Uh, and yes, the practice final, actually practice test seven, which is for online test seven, which is an extra credit test. That is essentially the same as the practice final exam, but I don't know why the practice final exam's not here. I made it, and I remembered the other day when I was in here, I noticed it didn't have any questions, but I corrected it that night, and now it's gone. So let me see if this is it. I'm looking at the modules in our class right now, and I think PFE, I think I've got it fixed now. Let me see.
I also wanted to ask about the extra credit for face-to-face test two.
Hmm.
Um, I saw in the announcement you said for the extra credit you had to get three scores above a 70. Is that
Hmm.
just for vectors or is that for all
Yeah, that was
exams?
just for the first one. The other ones, you just want to get as high as a grade as possible.
Okay, awesome. Thank you.
Yeah, no problem. Okay, so I now have the practice final exam open for you guys again. It was open before, but it didn't have any questions, so it wasn't very useful. But now it's opened again, and it's in the practice test module within Canvas, as it sort of always is. So hopefully y'all can make use of that. Anybody else have any questions? Looks like most everybody's here now. All right. So yeah, practice test '07, which is for the extra credit online test. That online test is a quote unquote extra credit online test because I'm now dropping your two lowest online test grades So you don't necessarily have to take this, but a lot of people derive a little bit of confidence by having completed a online test that's related to the chapters of the face-to-face test, so that if you take this before the final, you might have a little bit of a boost in confidence and abilities just from taking that first. But again, you don't have to take it. It's going to count as a zero, but I'm dropping the two lowest instead of one lowest. So that's uh, the way the math works out on that. Anybody else have any questions before we go ahead and get started?
Yeah, I have a question, Professor. How many points do you get added to our face-to-face test if we do the extra credits?
I mentioned that in one of the emails I sent, and here's the explanation. Basically, if you scored a 50 or lower and you get 100 on all three, then that'll bring your score up to a 67. If you scored only 50% on average for all three, then you'd only go 50% of the way from your grade to 67. So if your grade was a 50, literally a 50, and you only got 50% on the extra credits, then the difference between 50 and 67 is 17. So that would be 8 points higher, and your test grade would go up to a 58. So that's the way that works. But if you have a 51 to a 60, it can go up to a 77. If you had a 61 to a 70, it can go up to an 80. A 71 to an 80, it can go to a 90. An 81 to a 90, it can go to a 93. And students that make a 91 or higher have up to 2 points added to their score, and that's it. But that's how you get it. Is basically you get 100% on as your highest score on three of those, and take that first one three times at a 70 or higher, then you're qualified for the extra credit points. And I'll put those in probably by Monday or Tuesday of next week, the extra credit points for that. I
Okay,
want you to have it before you take the final, but I don't really care if you have it before you take the test, the face-to-face test three.
okay, gotcha. And then one more question. Do we have
Yes,
to
sir.
take a lab final exam?
No, no. In fact, my students have been doing pretty well. They've been obviously doing their own work and that sort of stuff. So it doesn't appear to be a need to take the online, or excuse me, to take the final exam for lab. So your grade's going to be basically what I'll have graded by Sunday this afternoon. Or this Sunday afternoon, I should have all your labs graded. Maybe one might be left, but that's pretty much it.
Okay, thank you.
You're welcome. Anyone else? All right, well, we're going to go ahead and get started. We were in chapter 14 last time, and we had worked example 14.3 was the last one. I need to get you a little bit up to speed on chapter 14 regarding some other examples. So I'm going to jump right in with example 14.4. Again, this is a really good time if you have your electronic book open. It's good for you to be able to look at that example as I work it. But the example we're doing is example 14.4, and it's asking us to estimate. This one and the next one are kind of neat little applications of simple harmonic motion. If you see something in real life that's actually repeating itself over and over, that could be something like, for instance, the full moon. You know the full moon is on a certain day, and then a certain number of days later it'll be a full moon again, and then a certain number of days later it'll be a full moon again. That's something that's repetitive, and it's repeating itself. Because of that repetitiveness or repeating itself, it sort of exhibits simple harmonic motion, and therefore you can sort of make simple harmonic motion type approximations to it, and they work out really well. So that's what we're going for here. So let me show you an example of this. It says spider web. A spider of mass zero point 0.3 grams waits in a web of negligible mass. A slight movement causes the web to vibrate at a excuse me, with a frequency of about 15 hertz. Estimate the value of the spring stiffness constant K for the web, and then B, at what frequency, thank you, at what frequency would you expect the web to vibrate if an insect of 0.10 gram mass is trapped in addition to the spider? So what we have is the mass of the spider is equal to 0.30 grams, which equals 3.0 times 10 to the negative fourth kilograms. We will need it to be in kilograms to make good use of it. We also know that the frequency is equal to 15 hertz, And what we want to know is the spring constant. That's for part A, K equals question mark. And then part B, if M equals ms plus m insect, which equals 0 point. Remember, the insect's supposed to be another zero point 0.1 grams, so zero point 0.1 in addition to zero point 0.3 would be 0.40 grams, which equals 4.0.
I don't know if it's just on mine,
Oh,
but
it's
it
not
doesn't have
showing.
zero. Yeah. Yeah, it
Thank you.
started panning around the room. We're looking at like the
No,
background for
that
a
that
second.
was that was your instructor being a very stable genius. I'm sorry about that. That was just
No, that's okay.
thanks for catching me, and I'm glad you caught it before it got too out of hand. But yeah, I'm sitting here writing up a storm like, oh yeah, this is great.
No, I just thought it was funny because it panned to the background and I was like,
Yeah, hey, look at the junk I got back here. Isn't that great?
yeah,
All
you don't
right.
want to see mine.
All right, so it's 4 times 10 to the negative fourth kilograms is the mass. Now, what we mean by all this is that we don't see any spring existing, but we know the spider web is going to do like this, and that's just like what a mass hanging from a spring does. So let's just treat it like one. So for part A, what I'm going to say is omega is equal to the square root of k over m. If I squared both sides, that would be omega squared is equal to k over m. So k must be equal to m times omega squared, and that's what I'm going to use. So I'm going to say 3.0 times 10 to the negative fourth kilograms is the mass. And then the omega is 2 pi times the frequency. That's another thing we're using. Omega equals 2 pi f. And since they gave us the frequency in hertz, we know that's an f, not a w, or not an omega. If it's omega, it should be in radians per second, or you might want to qualify it as not cycles per second because that's really hertz, but revolutions per minute would be another example, something like that. So if it's in terms of degrees or revolutions, you could probably assume that's going to be an omega. But if it's in units of hertz or cycles per second, you should assume that's an F. So in this case, I'm going to take 4 pi squared because omega's got to be squared and omega is 2 pi f. So the 2's got to be squared, the pi's got to be squared, and then the 15 hertz has to be squared. So that's going to give me K. And now I'll pull out my calculator. So I've got 3 times 10 to the negative fourth times 4 times 3.14159 times 3.14159. Obviously, a square would be quicker than that, but I'm not doing that. And then 15 squared, which obviously at this point I decided to go ahead and put a square on it. In this case, I get K is equal to 2.66, and that should come out in newtons per meter. As you can tell when you look at the kilograms and the hertz, a newton is a kilogram meter per second squared. So a newton per meter is just a kilogram per second squared. And if you take a kilogram per second squared and multiply it by a hertz squared, then the hertz is sort of dealing or dividing it by it. That gives you the newtons per meter. Anyways, I know I butchered that sentence, but I think y'all can follow what I'm saying. The units worked out like this. We basically had a kilogram times a uh, cycle per second times a cycle per second. So the cycle is kind of a weird, confusing part, but ignore that for just a second. What we have is a newton is equal to a kilogram meter per second squared, so that a newton per meter is a kilogram per second squared. And you can see that that turns out to be more or less a kilogram per second squared times cycles, which again, we can sort of throw that out here and there. But that's how the spring constant worked out for the spider webs. Everybody follow that part at least? Your book calls it 2.7. I'm carrying an extra digit like I always do for good measure. Now for part B, we want to find out what the frequency would be. And in this case, they're actually asking for the frequency, not the rotational frequency, not the rotational velocity or anything like that. So in this case, again, we're going to have omega is equal to the square root of k over m. But this time, the k is what we're using. The 2.66 is what we just found. So I'm going to use that as 2.66 newtons per meter, realizing that that second 6 is obviously not a sig fig. But, oops. But now I've got to divide that by the mass, and the new mass is 4 times 10 to the negative fourth kilograms. And now that's going to be completely omega. So, and then I have to use omega equals 2 pi f to get the frequency. So I'm going to take 2.66 and I'm going to divide it by zero point 0.4 times 10 to the negative third. That's just double checking to make sure 4.0 times 10 to the negative fourth is right. When I divide the 2.66 by zero point 0.4 times 10 to the negative third, I get 6,650. Now I'm going to take the square root of that by raising it to the 0.5 power, and that gives me 81.55, and that's actually two digits beyond the sig figs that I'm supposed to have, but that comes out in radians per second. We want f, and remember omega is equal to 2 pi f, so f is equal to omega over 2 pi, so that's going to be 81.55 radians per second divided by 2 pi radians, more or less, is what we're talking about. And we could call that radians per cycle. So that'll actually force the cycle to be back on top, and then you'll have cycles per second, which is what what hertzes mean. So I'm going to take this 81.55. I'm going to divide it by parenthesis 2 times 3.14159, close parenthesis, and that gives me 12.97, or I might as well call it 13.0 hertz. And that's the frequency of oscillation for the spider web when it's got a bug on it. So you can see in some sense that a spider could actually sense how much their spider web bounces, and from that difference in frequency, they can say, "Oh, this is going kind of slow. I'm thinking there's a creature on it, so it'll go walk around its spider web and look for the delicious morsel to eat, if you will." Anybody have any questions on that? Okay, something that's kind of important that I want to make sure you guys understand is you need to understand the parts of the solution of a simple harmonic oscillator equation. So, one of the things we did do was we found the simple harmonic oscillator equation. Remember, the simple harmonic oscillator equation is normally written like this: d2x over dt squared plus k over m times x is equal to 0. Or more generally, you might just say it's x double dot plus some constant times x is equal to 0. And what this implies is the solution is equal to x is equal to a cosine omega t plus phi, and omega has to be equal to the square root of whatever that c is in front of the x. That's the key thing here. So when we had it for a mass on a spring, we had k over m was c, and that's why the frequency became c. So now, with that in mind, I'm looking at exercise D. So this is an exercise, not an example. But in exercise D, they say x is equal to 0.80 meters times cosine. I'll put parentheses around it just to make it look a little less scary. Times 3 point, or cosine of 3.14 times t minus 0.25. That's the whole argument of cosine. Okay. So in this case, they're asking you, what is the frequency? So what is the frequency? And more specifically, I'd say, what is the frequency? I'd say, what is the amplitude? I'd also say, what is Vmax? I'd say, what is Amax? And I'd also say, this one's a little more obscure, but I want you to understand the term. So, what is the phase constant? In other words, in general, cosine is supposed to start at the argument of the cosine being 0. And when that's the case, the cosine spits out 1, and then it goes down till the argument of the cosine reaches pi over 2, at which point it's 0. And then it reaches the point at which the cosine uh, of pi is equal to -1, and then it comes back up at which the cosine of 3 pi over 2 is 0, and then back up to 2 pi, at which case the cosine of 2 pi is equal to 1 again. If you have a phase factor in here, or a phase constant in here, like I'm talking about now, then that's something that allows that cosine wave to either shift this way or this way, and that's what we're talking about. So I want to know what is the phase constant, and I'll remind you that phi is the phase constant here. So I'm actually souping this up a little bit from the exercise just so you'll know exactly what these things are. So remember, the solution is A times cosine omega t plus phi. So omega is equal to 3.14, and by default that has to have units of radians per second, because ultimately the 3.14t minus 0.25, all that has units of radians. And in order for the 3.14 to be multiplied by time and have it come out in radians, that means the 3.14 has to be in radians per second. But omega is also equal to 2 pi times f, so that tells us f is equal to 3.14 divided by 2 times 3.14, and that means the frequency is equal to 0.500 hertz. So that's what the frequency is for that, and that's all exercise D asked for. I went for more because I want you to recognize this in that x equals zero point 0.8 meters times cosine of 3.14t minus 0.25. We want to know what all those quantities are. So the next thing I'm going to ask you is, what is the amplitude? And we can see that the amplitude is 0.80 meters. And that means that actual the actual max x will oscillate back and forth between positive zero point 0.8 to 0 down to negative zero point 0.8 to 0, positive zero point 0.8. That's what the amplitude is, the 0.8. Okay, so I've got that. Now, what is Vmax? Well, we learned when we took the derivative of x with respect to time. Actually, let me keep writing that in red. Uh, when I took v equals dx dt, what happens is I get the negative 0.80 meters times 3.14 radians per second times sine of 3.14t minus 0.25. So we can see Vmax is this quantity. So that tells us Vmax is equal to A times omega, which is 0.8 times 3.14. And that gives me 2.51. So this is about 2.51 meters per second is Vmax. I also ask you, what is Amax? And that's what the Remember, Vmax was what the velocity bounced back and forth between positive Vmax, 0, negative Vmax, 0, positive Vmax. Well, A does the same thing. That'll be positive Amax, 0, negative Amax, 0. So Amax, when we take the derivative of V, then we get A, the acceleration. Don't know why I wrote that there first, but A is equal to dv dt. And taking the derivative of this, we see the derivative of sine is cosine, and the negative's already there, so we'll keep it. And this becomes 0. Actually, I'll go ahead and write down the new number since I already computed what Vmax was. I'll write 2.51 meters per second times 3.14 radians per second times cosine of 3.14 t minus 0.25. So that's our acceleration as a function of time, and that tells us A max is equal to A omega squared. So I'm going to take that 2.512 and multiply it by 3.14, and that's going to give me 7.89. And that's meters per second per second. And again, we lost 1 sig fig in that because the 0.80 only has 2 sig figs. So that's our Amax. And then finally, if we want the phase constant, and again, the main reason I'm asking you this is because I want you to know that term, phase constant, is the thing that's being added in the trig function. So it could be, omega t plus some number or omega t minus some number or something like that. So in this case, I'm going to just say phi is equal to 0.25, and the units there has to be radians, and that's what that is. Okay. So the big point here is one, it's definitely something I'm going to ask you about on possibly a online test 7, but definitely by the time we get to the final exam, that's a very fair question. As I give you a x as a function of time, tell you it's for a harmonic oscillator of some sort, and I ask you to identify the amplitude, I ask you to identify the frequency, the period, the max velocity, the max acceleration, the phase constant, all that kind of stuff can be asked. So I wanted to explain that to you. Not only that, I want you to understand where they come from. When you saw the differential equation, which is what we did when I said the differential equation is d2x over dt squared plus k over mx, once I took that equation and I said x is equal to a cosine omega t plus phi, that is a solution, but you're not done yet. You can't solve a differential equation. A first order differential equation you can't solve without one initial condition. A second order differential equation you can't solve without two initial conditions. A third order has to have three, and so on and so forth. So what you're supposed to do is you've come up with a general solution, but that should have two arbitrary constants in it because this is a second order differential equation. It's got a second order derivative. d2x over dt squared is second order. So the two arbitrary constants that have to be adjusted are the a and the phi. The omega is not arbitrary. That is defined by the differential equation. Okay, so that's always going to be the square root of whatever that constant is in front of the x on a simple harmonic oscillator equation. Any questions on that? All right. So I was looking in the lines here. I'm actually looking in the lines below exercise D. It says, let us continue our analysis of the simple harmonic oscillator. The velocity and the acceleration oscillating mass can be obtained by differentiation. That's more or less what I just showed you. You can see that V max is equal to omega times A. You can see that A max is equal to omega squared times A. You can even see stuff like x0 is equal to position x at time t equals 0. You can see v0 is the velocity at time t equals 0, and that becomes negative omega a. So let me just let you understand what we're saying there. So these initial, turn it, sorry about that. Okay. These initial conditions that we're talking about are normally something like x at t equals 0 is equal to some number. and that would be one of them. And the other one, hopefully, these are the two simplest, nicest cases. The other one is v at t equals 0 is equal to some number. Okay, if you have those are sort of the nicest ones you could have. But in general, it doesn't have to be that. What they generally say is x 0 is equal to x of t equals 0, which we could succinctly write x of 0 like that. But if you look at the equation that we said x was, remember x was equal to a cosine omega t plus phi, like that. That's supposed to be our solution to the differential equation. Uh, if you substitute t equals 0, you get a times the cosine of phi. So that's one thing that can help you figure out what phi is as well as what a is. Another thing we often have is v0. Remember, since x is equal to a cosine omega t, that says v is equal to negative a omega sine omega t plus phi, like that. So v0, which is v of t equals 0, which more succinctly is v of 0, is equal to negative a omega times the sine of phi. So that's another initial condition that we could make use of. In principle, that's not all. We could make use of some data about the actual acceleration. And of course, taking the derivative of this, we see a is equal to negative a omega squared cosine omega t plus phi. And now we could say a0 is equal to a of t equals 0, which is a of 0. That is equal to negative a omega squared times cosine phi, like that. So those are the ways we traditionally use the initial conditions. We'll have two of those more than likely, but you don't always have to have at time t equals 0. They could give you at time t equal 0.8 seconds if they wanted to. It just wouldn't be as easy. It's a lot nicer when it's 0 because all the omega disappears and that sort of thing. But what you can see here is we've got two unknowns, a and phi, and this is three different equations. We only need two of those to discern what a and phi is. So that's really the whole trick of solving differential equations. It's not just finding a solution that gives you 0 equals 0. You then have to make sure that solution involved, if it's a second order differential equation, it involved two arbitrary constants, and then two initial conditions will allow you to determine those two arbitrary constants. Any questions on that? All right, so let's look at example 14.5 now. So this is example 14.5, and it says a vibrating floor. This is another example where we can just arbitrarily say, hey, this thing seems to be acting like it's in simple harmonic motion. Let's use that to find out some facts about it. So a large motor in a factory causes a floor to vibrate at a frequency of 10 hertz. The amplitude of the floor's motion near the motor is about 3 millimeters. Estimate the maximum acceleration of the floor near the motor. Now, knowing Newton's second law, F equals ma, and that's the total force, the sum of all the forces is equal to mass times acceleration. You can see that, oh, if I knew the acceleration and then I had something that represents sort of the mass of that, for instance, that big motor or in the factory, if I had those two quantities, I could multiply them together, and that would give me something like a force. And as a structural engineer, that would be very relevant to make sure that this floor doesn't fall after a few years. So this is a very real physical problem that you could make use of. So what we have is the frequency was 10 hertz. And what we said was the floor is vibrating. That looks like a 20, so I'm trying to make it look less 20 like. Okay. And what we had was that the amplitude of vibration was 3.00 millimeters. They said the amplitude of the floor's motion. So what they're saying is when it's perfectly still, from that point, it goes up 3 millimeters and then it comes back to the ground, which would be zero height, and then it goes down 3 millimeters. You got to make sure that's the case because they could be talking about the total distance from the top swing to the bottom swing. That's twice the amplitude. In this case, they told us specifically the amplitude. So we know the amplitude is 3 millimeters, which equals 3.0. And actually, there I gave an extra sig fig. 3.0 times 10 to the negative third meters. So in this case, what they want to know is estimate the acceleration. Well, we know the max acceleration, A max, is equal to A omega squared. That's the magnitude of it. That's all we need. So I can go ahead and write this down as 3.00 times 10 to the negative 3 meters times 2 times pi times 10 hertz squared, and that's going to give me the actual max acceleration. So 2 pi times 10 is obviously 6.28, so, or excuse me, 62.8, because 2 pi, of course, is, or pi is 3.14, so 2 pi is 6.28, and then if I multiply that by 10, that's 62.8. So if I say 62.8 squared, and then I multiply that times 3 times 10 to the negative 3, that gives me 11.8 meters per second is equal to A max. So I could literally use that as a, if I was working as a structural engineer still, I could use that as a data point to say, okay, well, I have some estimate of roughly what's going on here. Maybe I'll add a safety factor to it, but I know as a bare minimum, it's going to be shaking like this. Maybe I say that it's a, acceleration of, instead of 11.8, maybe I say it's 11.8 and add 20%. And then I multiply that by a figure for the mass, and then I say, okay, let's imagine we have a point load here that weighs as much as this machine, or if the machine takes enough floor space, we could say, okay, it's a distributed weight over the whole surface, or we might look at the details of how the motor's built. We might find that it's got four little legs, and therefore all the force is equally distributed amongst those four, so we have 4 point loads, and then we could make sure that we shore up the beams, the joists in the floor to make sure that that holds. That's the kind of stuff you'd get from statics once you take statics in engineering. So, anybody have any questions on this? Example 14.6 is more or less the same thing I just did with example D, so I'm going to leave that one be. Example 14.7, the cone of a loudspeaker oscillates in a simple harmonic motion at a frequency of 262 hertz, also called middle C. The amplitude at the central part of the cone is A equals 1.5 times 10 to the negative fourth meters. And at t equals 0, x is equal to A. What equation describes the motion of the center of the cone? B, what are the velocity and accelerations as functions of time? And C, what is the position of the cone at t equal 1.00 milliseconds? So this is a case where we're actually given data that hopefully can help us figure out the whole solution. So this is example 14.7. Remember 14.6, we've already done something just like it. So what we have is the cone loudspeaker oscillates with a frequency F is equal to 262 hertz. Again, that's middle C. For those of you who are musically inclined, we know that the amplitude, they've already given us one of the constants by doing that. So that means they only have to give us one other equation or one other constant, and we'll have the x of t completely defined. But A is equal to 1.5 times 10 to the negative fourth meters. And then we learn at t equals 0, x is equal to A. So that is another initial condition, and that allows us to figure out probably the phi. Okay, we know the solution is x of t is equal to a cosine omega t plus phi. That's the general solution for anything obeying simple harmonic motion. Now we have the a because they gave it to us, so I can go ahead and write this as 1.5 times 10 to the negative fourth meters times cosine. Now here's the omega part. The omega is equal to 2 pi times the frequency. So that's going to be 2 times pi times 262 hertz, like that. So in doing that, I say 2 times 3.14159 times 262. This is a really big number. It comes out to be 1,646. And that is radians per second. So this becomes 1,646 radians per second times t plus phi. Okay, so that's what our x of t is so far. What we need to figure out is what is phi, and what we know is x of 0 is equal to a, and that tells us, oh, okay, a, which is 1.5 times 10 to the negative 4 meters, is equal to 1.5 times 10 to the negative fourth meters times cosine of, now we've got t equals 0, so this is just 0 plus phi. So what that tells us is we can use the inverse trig function to figure out what phi is, because it's obvious that the cosine of phi must be equal to 1, because I can divide both sides by 1.5 times 10 to the negative 4 meters. 1.5 times 10 to the negative 4 meters, and that's going to give me 1 is equal to cosine phi. Therefore, we can say phi is equal to 0, or plus or minus uh, plus or minus 2 pi, or plus or minus 4 pi, all sorts of choices. Obviously, the most simple case would be phi equals 0, so I'm going to choose that. So it asks what equation describes the motion of the center of the cone. So we're now in a position we can write that. X of t is equal to 1.5 times 10 to the negative fourth meters times cosine of square bracket 1,646 radians per second times time. And that's it in its entirety, because the phi, the phase angle, turned out to be 0. Oops, I switched to red on purpose and it didn't change it. So there's part A. Part B says, what are the velocity and acceleration as functions of time? So B, v of t is equal to dx dt. And obviously, you can take that 1.5 times 10 to the negative fourth and multiply that by 1646. And that gives us a slightly different number. That gives us a number of 0.2469. So now when I take the derivative of cosine, it's going to become negative sine. And then I got to take the derivative of omega t, and that's just going to be omega. So I'm taking the omega, multiplying it by 1.5 times 10 to the negative fourth, and that's what gave me 0.2469. Now, we only had 2 sig figs in the acceleration, so I can only have 2 sig figs here, and that should come out in meters per second, and then times the sine of 1,646 radians per second times time in square brackets. So that's our velocity as a function of time. Our acceleration as a function of time is going to be the derivative of that. So a of t is equal to dv dt, which equals negative. Now I've got that 0.2469 times 1646, and that gives me 406. So this is going to be now negative 406.4. Again, we only had two sig figs, but now it's meters per second per second. That's the what we would normally call the amplitude, but we know it's actually the acceleration max or a max. And of course, when we took the derivative of sine, we got cosine, and the negative was already there, so we had to leave it there. But we still have 1646 radians per second times time, and that is our acceleration as a function of time. Now for part C, they want to know what is the position of the cone at t equal 1 microsecond. So I'm going to do that now. C, they want x of 1.00, actually I said micro, I mean millisecond. So that is going to be 1.5 times 10 to the negative fourth meters times cosine of 1646 radians per second times 1.00 times 10 to the negative third seconds. Now, the key thing here is this has to be in radians. So I'm going to take the 1646 and multiply it by 1 times 10 to the negative third, and that gives me 1.646. That's supposed to be in radians. So what I'm going to do is convert it to degrees so I don't have to change my calculator mode. Okay, so I'm going to multiply that by pi and then divide by I'm going to multiply that by 180 and then divide by pi, and that'll give me what I'm taking the cosine of. So I'm going to say times 180, and then I'll say divided by 3.14159, and that gives me the inverse the cosine of 94.308 degrees. So I take the cosine of that, and now I multiply that by 1.5. Actually, I can't do it that way. I say 1.5 times 10 to the negative 4 times that previous answer, and this gives me negative 1.13 times 10, getting very, very small in this little corner here. So times 10 to the negative 1, 2, 3, 4, 5, 10 to the negative fifth meters is the actual position at 1 millisecond. Uh, So if you look at the answers the book has, it has omega. Well, it actually still it used 1650 instead of 1646. That's okay, but it gave the same function 1.5 times 10 to the negative fourth meters times cosine 1650t. It gave us the same function for v, the same function for a, and it says negative 1.2 times 10 to the negative fifth for the actual displacement at t equals 1 millisecond. So everything's pretty close. I would have rounded that to 1.1. They rounded it to 1.2, but that's probably because they used 1650 instead of 1646. Any questions on that? Okay, so these types of calculations are the most critical part that you should be able to do. I'll tell you to look at, for instance, example 14.8, but these examples, 14.1 through 14.8, are sort of the most bread and butter types of examples. Something else that we want to cover as well is actually, I'm going to do 14.9 so you can get a real appreciation for what happens when you actually try to evaluate the initial conditions. So let's go to example 14.9. Again, me skipping those examples is not me saying you don't need to know them. You absolutely need to know them. But it's me saying, hey, I've done enough on these other examples. You should be able to fill in that gap. They're pretty straightforward. So this one says spring is started with a push. Suppose the spring of example 14.8 is compressed 0.100 meters from equilibrium. That is, x is equal to negative 0.100 meters, and is given a shove to create an initial velocity in the positive x direction of 0.400 meters per second. Excuse me. Determine A, the phase angle, B, the amplitude, C, the displacement x as a function of time, x of t. Okay, so we're supposed to use the example from 14.8, and I'm trying to remember which one that was. It looks like it's the example that I just skipped. That's super helpful. Crap, crap, crap. Okay. Bop, 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 bop. I tell you what, let's back up. Let's erase that 9, and I'll go ahead and do 8, and then I'll do 9 as well. So in this case, we got a spring stretches 0.15 meters when a mass of 0.300 kilograms is suspended from it. So x is equal to 0.150 meters when mg is 0.300 kilograms times 9.80 meters per second per second. This is because the mass is hanging and the force isn't 0.300 kilograms because the force is not measured in kilograms, it's measured in newtons. So in order to make that mass into a force, we got to multiply it by 9.8. So 0.3 times 9.8 gives us 2.94 newtons. And that's how many sig figs we have. So we're going to call that 2.940 newtons. So that's that. And it says the mass is gently suspended from it, as in figure 14.3b. The spring is then set up horizontally with the same mass. Thing is, first we hung this mass vertically from a spring, and that allowed us to determine K. Now we're going to take that mass and lay it over horizontally on a frictionless surface, and we're going to put that thing in motion. The mass is pulled so that the spring is stretched by 0.100 meters from equilibrium and released from rest. Determine all this stuff. Okay, so now I have to say m is still 0.300 kilograms. In this case, they were nice enough to use the same mass. Be attentive to that. They can give you one mass to hang from it, and you use that to determine K, and then they put a different mass on it when they put it horizontally, and then you have to keep track of which mass you're dealing with. So pay close attention to that. In this case, it wasn't a big deal. Then we said they pulled the mass so that the spring is stretched. So X equals positive 0.100 meters. The mass is pulled so that the spring is stretched 0.100 meters from equilibrium and released from rest. So this is at t equals 0. And they said it was released from rest, so that says V of 0 is equal to 0. So notice how they use sentences to tell us the two initial conditions without actually stating them as equations in any way. That's something you've got to figure out physically. So what they want to know in part A is K and omega. So K equals question mark and omega equals question mark. In part B, they want to know the amplitude of the horizontal oscillation. So A equals question mark. In part C, they want to know Vmax. In part D, they want to know Amax. In part E, they want to know the period. and the frequency. In part F, was a lot of stuff. In part F, they want to know x of t. And then in part G, they want to know the velocity. So G, they want to know v of 0.150 seconds. So that's what we're trying to figure out here. So let's start off to figure out what K is. We have F is equal to negative KX. As I told you, if you're plugging Hooke's law into another equation, it's absolutely essential that you put that negative in. But if you're just trying to calculate X or K or F, you can drop the negative. So in this case, what I'm going to say is 2.940 newtons is equal to K times 0.150 meters. That tells us that K is equal to 2.940 divided by 0.150 gives me 19.6. And that turns out to be newtons per meter, obviously. And then omega is equal to the square root of K over M. So that means the square root of 19.60 newtons per meter divided by the same mass. Remember, this is the case where I told you, watch out, they might have a different mass. So with that in mind, I'm going to take 19.6, I'm going to divide it by 0.3. That gives me 65.33. Now I'm going to raise that to the 1/2 power because I was taking the square root, and that gives me 8.083 radians per second is omega. So our angular frequency is 8.08 radians per second. Part A, they want to know the amplitude of horizontal oscillation. Well, the fact that they stretched it at a 0.1 and then let it go tells you that there's no way in heck it's ever going to get higher than 0.1. And if it had friction, it would get smaller and smaller and smaller. So obviously, the initial x is really the amplitude. So that's the reasoning that goes into that. Notice I didn't use any equations, I just used reasoning. So A is equal to x is equal to 0.100 meters. And I'll call that x0 just to be a little more concrete about what I'm doing. So that's what the amplitude is. And that's all they needed for that part. For part C, we want to know Vmax. And we know, for instance, that Vmax is equal to A times omega. So we can just take that 8.8083 and multiply that times 0.1. And you don't even have to do that math. That's 0.808. So 0.8083 meters per second is Vmax. They also wanted, that was part C. So part D, they want A max. We're up to that as well. So A max, we know that's A times omega squared. Again, we knew that because we took the derivatives and we saw that when you take the derivative of A cosine omega t plus phi, you get A omega times negative sine omega t plus phi. So the A omega was the Vmax, and we took the second derivative. We got negative A omega squared, so A omega squared was the A max. So in this case, we're going to take 0.1 and we're going to multiply it by 8.083 times 8.083 and oops, 8.083. Yeah, that works. So this gives me 6.53. And one extra digit would be a 3 on the end. That's 6.53 meters per second per second. That is our max acceleration. Everybody follow how I'm getting this A omega and this A omega squared. That all makes sense, hopefully. Okay. Let me make sure my chat's open, so in case anybody's typing anything to me. It does not appear to be anybody typing anything. All right, so part E, it wants to know the period and the frequency. So E, we can say the frequency is omega over 2 pi. So I can take the 8.083 and divide it by, I'm going to divide that by 6 point, well, I'll actually just divide it by 2 pi. So 8.083 divided by parentheses 2 times 3.14159. Making sure I use at least enough sig figs. So this is going to be 1.286. And that's hertz. So that's the frequency. And the period, remember, the period t is 1 over the frequency, just like the frequency is 1 over the period. So if I raise this to the negative 1 power, then I'll get 0.7773 seconds. And that is the period of oscillation. So that's some of the stuff we're trying to make sure you guys can figure out. Part E was that. Now we're going to do F. The displacement is a function of time. So F is pretty straightforward. X of t is equal to the amplitude. So that's going to be 0.100 meters times cosine omega. We found out that was 8.08 with one extra sig fig radians per second times time, but there's also a plus phi. So we've got to figure out what that plus phi is. What we did discover was that V of 0 is equal to 0, and we should be able to figure that out as well. So V of 0 is equal to 0 means, remember we figured out V max, so V is equal to V max, which is 0.8083 meters per second negative times sine 8.083 radians per second times time plus phi. So if we plug in t equals 0, we get 0 is equal to negative 0.8083 meters per second times the sine of phi, because obviously t being 0 means the omega t term is 0. So we can now say evidently phi is an angle that makes sine equal to 0. In this case, we could say, oh, well, sine of 0 is 0, so that works. So we can say phi is equal to 0. We could also say it's plus or minus pi. We could also say it's plus or minus 2 pi, but I'm going to choose the phi equals 0 case. And with that, I can now say that x of t is equal to 0.100 meters times cosine of 8.083 radians per second times t, and there's no phase angle, or the phase angle is 0 is another way of saying that. So that's our displacement. And now finally part G, they would like to know the velocity at t equals 0.150 seconds. We just figured out what the velocity was, so I'm going to go ahead and plug that in. I get negative 0.8083 meters per second times the sine of 8.083 radians per second times 0.150 seconds. Again, this is a case where we're supposed to be using radian mode. It's a pain in the butt to change the mode of my calculator, so I'm just going to convert the 8.083 times 0.1150. I'm just going to convert that to degrees. So 8.083 times 0.150 gives me 1.21245. Now, what I'm going to do is I'm going to multiply that by 180, and then I'm going to divide it by 3.14159, and that's going to convert it to 69.46 degrees. I'll take the sine of that angle, and that gives me 0.93647. Now I'm going to multiply that by 0.8083. And it's technically a negative, so I'll remember to throw the negative sign on it. So what I get is the velocity at t equals 0.150 seconds is v of 0.150 seconds. I'd really like to just be able to write it as v of 0.150, but I always write it a second time just to make sure everybody knows what I'm talking about. So this is going to be negative 0.7570, and that is in meters per second. And that should be the velocity at 0.150 seconds. If I look at my answers and compare them to the answers from the book, it got 19.6 for K, it got 8.08 for omega, it got A was zero point 0.1, it got Vmax was 0.8083 or 0.808. It had Amax was 6.53. I had 6.533. It had F was 1.29 and T was 0.777. All of that looks like the same that I got. And finally, it got the velocity at that particular time was negative 0.756. So that looks good to me. Anybody have any questions on that? Okay. So now we can jump to example 14.9. By the way, we have a lab time meeting tomorrow. I'm going to probably finish up do more or less all of 15 and maybe even some of 14 then. And that way you'll have that video down. And if you guys want to show up on Monday, or Wednesday, that's purely going to be a review time. So that's a time where you can come in, ask me questions. We'll solve problems. You can pick out problems that you've seen on old tests. We'll solve those. Any of that kind of stuff is fair game. So by tomorrow, once I finish that lab session, there will be a video that I post, and that video should finish up what's necessary for chapter 14, if there's anything necessary, and then we'll go into chapter 15. And if that's not enough, I'll do another video. But the main thing is next week on Monday and next week on Wednesday, I'm going to be here as a time to answer questions, but I'm not going to be lecturing. Okay, that means you're welcome to attend, but you can also not show up if you won't. I'm not going to count that against you or anything. All right, so 14.9 says spring is started with a push. Suppose the spring of example 14.8 is compressed 0.100 meters from equilibrium and is given a shove to create the initial velocity of 0.400 meters per second in the positive x direction. Determine the phase angle, the amplitude, and the displacement. So that's what they want to know. So what they're saying is x of 0 is equal to, it's compressed, so that's going to be negative 0.100 meters. Notice compression we define to be in the negative x direction, and pulling it out we define in the positive x direction. That's just normally what we do. It's not like a big convention or anything, but if they say that, that's what you're going to go on the assumption of. Okay, so x0 is that. We also know that v of 0, which we call V0. By the way, this one's also called X sub 0. But V sub 0 is going to be positive 0.400 meters per second. And what we want to know is phi, we want to know A, we want to know X of t. Those are the three things we want to know. Okay? So we know X is equal to A cosine omega t plus phi. That's what it is. Okay? Now, we already know omega is equal to 8.083 radians per second is omega. We can't use the phi and we can't use the A, but we can use the omega. So that part's covered. Now, if we take x of 0 equals negative 0.100 meters, that means negative 1.00 meters is equal to A times the cosine of 8.083 radians per second times 0 plus phi, like that. Okay? Now, with that in mind, that tells us that negative 0.100 meters is equal to A times the cosine of phi. So I'm going to call that equation 1. Now I'm going to take the initial condition. We know V is equal to negative A omega times sine omega t plus phi. That's what V is. So if I want to apply that initial condition, that means positive 0.400 meters per second is equal to A times omega, which is 8.083 radians per second, times, in this case, it's going to be the sine, and also I have a negative out in front of this, so I better watch out for that. So it's going to be sine of, now remember, this is the time t equals 0, so it's just going to be the sine of phi, like that. Okay? Now, this is going to be equation 2. Now, it just so happens that a really smart thing to do here is to divide 2 by 1. So I'm going to say divide equation 2 by equation 1. When we do that, what we're going to get is 0.400 meters per second is equal to negative A times 8.083. That's supposed to be radians per second, and I almost wrote it as meters per second, and I almost wrote it as meters per second again, times the sine of phi, but we're going to divide that by equation 1, which is negative 0.100 meters. And this meter is, of course, equal to A times the cosine of phi. Okay, there's no number out in front. So what we see is happening here is I'm going to get negative 0, or excuse me, negative 4, and you could call that radians per second, negative 4.00 seconds to the negative 1 power is equal to, notice the A's cancel out, the meters canceled out there as well. The A's canceled out here. That's going to give me negative, and then sine theta over cosine theta is, in fact, tangent theta, or excuse me, tangent phi. So that tells us that phi is equal to the tangent inverse of 4.00. So if I take the inverse tangent of 4, I get phi is equal to 75.96 degrees, but I really need that in radians. So I'm going to take that 75.96, I'm going to multiply it by 3.14159, and I'm going to divide it by 180, and then that gives me 1.326 radians. So now I've figured out phi. And with that, I can plug that back into either expression, and that'll get me A. So plugging phi into, let's plug that into equation one because that's the simplest. When I do that, I get negative 0.100 meters is equal to A times the cosine of 1.326 radians. And that means A is going to be negative 0.100 meters divided by cosine of 1.326 radians. I'm going to, of course, use degrees because don't have to mess with it. So I'm going to take negative zero point 0.1 and I'm going to divide that by cosine parentheses 75.963 degrees, and that gives me negative 0.4123 meters. Notice the meter came from the unit on top. So now that I have that, I can now say all the things that they wanted to know. Phi was equal to, where did I write that down? Phi was equal to 1.326 radians. That's one answer. A is another answer. And we just figured out that A is negative 0.4123 meters. That's another answer. And they wanted to know, in addition to that, x of t. So x of t is just negative 0.4123 meters. I'll put that in parentheses times cosine 8.083 radians per second times t plus 1.326 radians, like that. And that's our x as a function of time. Now, just for to check on it, they got phi is equal to 3.60 radians. I don't know why that came out differently. But everything I did was, oh, okay, I see. They ended up adding 180 to it because it became a weird angle, but that's okay. Uh, oh, that also gave them a different amplitude, but either way, that's good enough. The way I did it was fine. I don't know. I'm not seeing exactly what changed it, but in general, the method is the following. If you want to have your initial conditions, basically your initial conditions are almost always x of 0 is equal to, basically a times cosine of phi, and then v of 0 is equal to negative a omega times the sine of phi. And if you want to deal with these, you can deal with this just generically, like I'm doing right now, by taking v0 over x0 and of course setting that to negative a omega sine phi over a cosine phi. You can see now that the a's cancel out and you end up getting, in fact, tangent phi is equal to V0 over omega x0. So this is an expression that you're certainly welcome to use. I'm not putting it on your equation sheet, but it's certainly reasonable. And if you do this one, you're going to get exactly the answers that the book had. There is some ambiguity in it. You could actually have it a little bit off, have it a little bit different. So you can adjust the amplitude. It'll change to one number, but if that changes, then the phase angle has to change. And then you can also try the same amplitude, but that'll give you a different phase angle as well. Now that we have that though, we can then plug it in either result, and that would give us a way to figure out what A is. And the way we do it is we imagine a triangle, a right triangle, and the angle phi is right here, and tangent is equal to opposite over adjacent. So I'm going to say tangent of phi gives me V0 over omega times x0, and then that means this right here is the square root of V0 squared plus omega squared x0 squared, like that. Now, with that in mind, you can say that cosine phi is equal to adjacent over hypotenuse. So that'd be omega x0 over the square root of v0 squared plus omega squared x0 squared, like that. And then that means x0 is equal to a cosine phi, means x0 is equal to a omega x0 over the square root of v0 squared plus omega squared x0 squared under the square root, like that. So you can now solve for A. What we found is A is in fact equal to x0 times the square root of v0 squared plus omega squared x0 squared, and then divide all that by, you can see the x0 actually cancels out. Oops. You can see the x0 actually cancels out. So I'm going to go ahead and erase that now. And what we're going to have instead is just all this divided by omega. Yeah, that looks right. Oops. And of course, you could force that inside, and you get the square root of v0 over omega squared plus x0 squared. So any of those expressions would be fine for finding out what phi is and what a is, but that just is a brute force way of working it, and it works every time. Now, the big important thing to figure out for the rest of this chapter is if you look in the next section, it says energy of a simple harmonic oscillator, and they give you these nice little equations to use. The main thing is the total energy can either be 1/2 k times a squared, because a is the maximum x it'll stretch. So if you stretch it a maximum amount and then let it go, then it only had potential energy. So the total energy was 1/2 k a squared. However, if you instead left it at equilibrium position and then give it a big smack and gave it an initial velocity, then you'd have the initial energies just 1/2 m v0 squared. Either way, E is going to equal 1/2 k a squared, or it's going to equal 1/2 m v0 squared, or it could equal, get this, 1/2 k x0 squared plus 1/2 m v0 squared. That's the total energy. So one of those three expressions are going to be it. Like the one we just did, that one had an initial position and an initial velocity. So we'd have to use this 1/2 kx0 squared plus 1/2 mv0 squared. If we started like the previous one, where we basically just stretched it out a certain distance and gave it a velocity with no stretch, then we just have 1/2 mv0 squared. But if we just did a stretch and let it go, then we just have the 1/2 ka squared. But either way, the total energy is equal to 1/2 k x squared. And remember that x is not just x, that's technically x of t squared, plus 1 half m v of t squared. That's going to be equal to either this or this or this will go here, or that'll go here, or that'll go here. And when you do that, you can find these neat little expressions like your book has given you, like v is equal to plus or minus the square root of k over m a squared minus x squared. So if you know any particular x, you can plug that in and find out what the velocity will be at that point. Or you can say, alternatively, v is equal to plus or minus v max, because remember, v max is a omega. So we could factor out that k over m square root and the a. And when we did that, we'd get the square root of 1 minus x squared over a squared. So both of those expressions are things we can get just from considering the energy. Not only that, if you look further, you'll see that this simple harmonic oscillator equation applies to rotational uniform circular motion. Exact same equations, exact same x position. It applies to a simple pendulum if we make the assumption that sine of theta is equal to approximately equal to theta. Then you end up get this, you end up getting x double dot plus, in this case, it's going to become uh, g square root of g over L. So this is g over L times x equals 0. That's for a simple pendulum. So it's the exact same equation. You could call it x, but instead they're going to call it theta plus g over L times theta is equal to this. So they're going to say theta equals theta max times cosine omega t plus phi, where omega is equal to the square root of g over L. Okay? That's the beauty of the simple harmonic oscillator equation. It pops up over and over and over again. And the next one, for instance, it does is a physical pendulum and then a torsion pendulum. So if we had a physical pendulum, the only difference is omega is going to turn out to be the square root of mgh over I, where I is the moment of inertia of the physical pendulum, and h is the distance from the pivot point of the pendulum to the pendulum center of mass. And m, of course, is the weight of it. If we had a torsion pendulum, the only difference is the omega would turn out to be another spring type constant, but it's a slightly different value. So we'd get omega is equal to the square root of k over I. So the same solution works for a torsion pendulum, a physical pendulum, all that stuff. You guys are free to go. Time is up. I'll wait for the last person to leave in case anybody has any questions. And like I said, I'm going to try to knock out the rest of this in 15 and tomorrow. And you guys have a nice weekend and start, getting prepared for your online test as well as your final exam. The good news is, other than chapter 14 and 15, preparing for this face-to-face test 3 covers everything but 14 and 15. Anybody have any questions?
Thank you. Have a great night.
You too, Michelle. Have a good one. How's it going, Riley?
Good. How are you doing?
Not too bad. What can I help you with, sir?
So the face-to-face test three, which I'm scheduling to take at a testing center for Tuesday. Sorry, I
Okay.
didn't email you that.
Oh, that's
But
no problem.
it doesn't cover chapter 11, right? It's
Right.
just
I just
9
went
and
through
10 are
10.
added on.
Yes, sir.
Okay, cool. Awesome.
Yeah,
I
that would make
appreciate
it
your
kind of
time.
ugly. Thank you. I should have said that. I'm glad you asked me that, so it's on the recording.
Yeah, I was like, oh, wait a second.
No problem. Yeah, sorry about that. And if you could just text me, let me know that you are taking it. Then I have a little form that I'm keeping just so I can know if any students are not signed up to take the test, so I can catch up with them. So still send me a text message or an email so that I'll know when you're planning on taking it, and I can put it on that sheet. I'd appreciate it.
Okay, yeah, I'll send a message through Canvas in
That's
just a
cool.
few minutes.
We'll do it with regular email, not Canvas. Half the time, I don't even get the emails through Canvas.
I got you. I got
That's why I said
you. Okay,
either
yeah.
texting or emailing. But
Okay,
thanks for
I'll
that,
send
Riley.
a email though.
No problem. Did you have another question?
No, that was it. Just wanted to clarify on that.
Okay. Let me know if you have any questions between now and the next time. Like I said, we'll meet Monday. It's optional. And we'll meet Wednesday. That's optional as well. But I will be there in case anybody has any last minute questions.
Okay, I'll probably be there in both of them, which is like a list of like old
Questions.
test questions or something like that. Yeah.
That's cool. That's cool. That'd be the perfect thing to do, and I want that on a video so people can help see it, even if they're not able to make it.
All righty, sounds good.
All right. See you, Riley.
See you. Hope you have a good weekend.
You too. How about you, Benjamin? You got a question, sir? I don't think nope, he's not here. All right. So I'm going to stop sharing and tell everybody bye bye. Thanks for coming.